When I start getting to Lewis dots, then that's okay.
Nope, starting now.
Got a beaker. You want to put salt in it. You want to dissolve salt. You add salt, stir it, dissolves, add salt, stir it, dissolves, add salt, stir it. At some point, you can't dissolve any more salt, right? And the simple test is you add the salt, you stir it, and it doesn't dissolve, it just sinks to the bottom. That is a saturated solution. Saturated is like a thin line. Anything below that line is unsaturated, right? So if you can dissolve more, then that's an unsaturated. Simple test, you add some salt, stir it up, it dissolves, it's unsaturated. Okay? All right. I'm thinking, Supersaturated. Supersaturated is when you dissolve more than the saturated amount.
Explain.
In high school, I love it. They just write that on the test. And I just sit back and wait for some head scratching. And the tilted head kind of, they start thinking, how's that possible? That's not possible. You just said saturated is when you dissolve as much as possible, but supersaturated, you dissolve more. What you have to do is you have to heat it up. And then, because solubility depends on temperature. You change temperature, you change the solubility. So, supersaturated, you heat it up, you let it cool down slowly, but it's unstable. All right? Your solutions right there are an example of a supersaturated solution. It's got a little thingy in there. You might want to record it on your phone if you want. Click that little thingy there inside. Everybody got one? Click that little, there's a thingy in there.
Oh.
Wait, what?
Oh, it's hot.
It was hot. Hey, but what about mine? Push the button.
It's
You have
childproof.
to like bend it.
It's childproof.
Bend the button.
You click
Bend
it.
it.
You have to click it.
Oh. Ow.
They use things in yellow.
Supersaturated solution.
That was cool.
Just click this thing. Okay. Want me to do
They
it?
use them to heat up.
Oh, it's already done.
Oh my goodness. It's like hot hands.
This is hot.
It's a hand warmer.
This is hotter than hand warmer.
It's hotter than a hand warmer.
That particular one. Does that one have WKEF on it? Channel 22? No, it's on the
Heat
cover.
and a clip.
It's on the cover. It's gonna, my brother gave me a bunch of these. He works at a TV station. He's got it as a promotion. I'm like, I'll take them. I'll be using them. I used to just do one in front of the class, but then I got to the point where I bought them. They're hand warmers. But what happens is, you can hold, I want them back. You can hold them as long as it holds heat. You can have them, but I want them back when the heat's gone.
Where do you get these?
Yeah, Google.
Amazon?
Wait,
I'm
am I
sure-
allowed to like move this way?
All you have to do is like,
Am I allowed to like move this way?
It's like a
Yeah.
slushy.
it's a slushy right now, but after a while it just hardens up and then cools off.
Oh.
And then what you do is you put it in boiling water
Yeah.
till it dissolves. It absorbs the heat. You take it out. You don't adjust it. These are reusable. The ones in the orange packs, one use. It's a chemical reaction. This one's a reversible reaction. And you can keep going back and forth.
What's the metal in here? Are you going to explain this more?
If you have a supersaturated
I
solution,
feel yours.
Hi. Yours is really hot.
Yeah.
Jeez Louise.
mhm.
That one feels fun. Okay, super.
If this is a supersaturated solution, all you have to do is add one crystal for a test, and the whole thing just crystallizes out. So I've heard that what it does is when you click it, it exposes a seed crystal, and then it just all comes out. I was at the mall one time, and there was a kiosk, and they were selling these things for $10. You can get them for $3 or $4 somewhere, but you might have to buy half a dozen of them. They were selling them for $10, and I went up, I played stupid, not tough. How's this work? And I wish I'd recorded her explanation because it was totally wrong. It was totally, she said it released oxygen or something, and I'm like, no, it doesn't.
So it's got grooves in it. So does it hold on to like a granular of the substance?
That's a good question. I think you just need a rough surface too. That went black. Is it okay? Is that all right?
I don't know. Maybe it's still recording. I think.
Okay. I think it's just rough surface
Yeah.
will do it. You can have super cooled water, and you can just agitate it, and the whole thing comes out. You
Mhm.
can. That's another lesson for another day. But that's a super saturated solution. Those are cool.
On the hottest day of the lab, you bring us these.
I just happened to find them in my basement. I'm like, well, I gotta take these in. I gotta take these in and show them because I couldn't find them for the longest time, and I found them. So
Happy for you. Happy for us.
yes, those things are cool. Everybody loves those.
Really cool.
They're just a really, really cool demo. It's a super saturated solution. You can buy these like I've seen them this big.
Whoa.
Like people use them for their bats or something.
Oh.
Have you seen them that big?
No,
Are they that big? And,
Yeah, they're really just to warm up scoops. So they're really like this long without water.
yeah, but it has a little clicky thing in it.
Mm-hmm.
It's a super saturated solution.
Huh.
And it's probably sodium acetate. That's the popular one that they have, that they use for that. Okay. Okay. All right. That I assumed that would be in 101 somewhere along the line. I want them back when you're done. I got a couple more that haven't been clicked because people don't come to class. All right. First thing you got to learn Lewis dots. Now you got to start copying.
Thank
now
you.
got to start writing that stuff down. I'm gonna teach for about an hour. Or you can take pictures.
I already did
All right. Lewis dots, or sometimes called electron dot diagrams. They show valence electrons. Did you do this yet?
that. Yes.
Did I do it?
No.
Okay. Sodium is in group 1. The number of electrons for sodium is 2, 8, and 1. You know what I mean? 2 in the first shell, 8 in the next shell, 1 in the... You just want the outer shell valence electrons. Everything in group 1, hydrogen all the way down to francium, or francium, I've heard, all has 1 dot. Everything in group 1, 1 dot. This is easy. All you need is your periodic table. Everything in group 2, 2 dots.
Boom.
2 dots. Okay? Everything in...
Just started.
I just started.
Okay. Oh, wait, sorry.
Give it a hot pack.
aluminum's got 3.
Yeah, three.
Transition metals.
I'm using the Arnold.
Transition metals, lanthanide, actinide, all have 2. There are some exceptions that are 1. We don't have to mess with that. All those in the middle, 2.
Does that have something to do with why, like, when they're full, it's 10?
Because if you do the electronic configuration, for example, for SC, right after calcium, calcium is 4s2, the next one's 3d1, 4, 3.
Got it. S. Okay.
So the D's are always 1 less than the S.
Say that again.
The D's are always 1 less than the S's. So if it's 4s, it's 3d. If it's 5s, it's 4d.
Right.
They're always 1 less. And
Okay.
the F's are 2 less. Anyway, yeah, those are not, D and F are not outer shell electrons.
Okay.
Transition metals, lanthanide, and actinide are not outer shell electrons.
So the outer shell electron goes.
Are just
from-
S's and P's.
Just S's and P's and always 2. Okay.
So, 1, 2, all these 2, 3, 4, 5, 6, 7, 8. With one exception, helium only has
2.
2.
And it's
But
fully satisfied.
It's not, yeah, but it has a full octet. That's why it's put there. The properties of it put it more here than it does here. Everything else, 8 in the outer shell. So it might be 2, 8, 18, 32, 8, and 2, something like that. So they're just talking about the outer ones. Their properties depend on valence electrons. If they have the same number of valence electrons, they have similar properties. Okay? All right. Now, where did I put my red? Okay. Now, about this time, somebody starts asking where they go. Did you do the arrows up and down?
Yes.
Yeah.
The orbital filling diagrams?
Yeah.
It's based on that. And I'm not going to get into that right now, but it's based on the orbital filling diagrams.
Well, I have a question
Oh.
because maybe you're going to cover this. Maybe I should wait till you
Go
say
ahead.
it.
Go ahead.
But in the book,
it has the way to do it, like counterclockwise, you know,
Yeah.
it tells you the way to do it, but then in one of the modules, it's like, it doesn't really matter.
Yeah.
So
Right.
like, which one, what's the
Okay.
answer?
What's the answer? All right. So, what happens is, when you're doing the electronic configuration, you're doing like, sodium, what is that? That's 3s. Let's do aluminum. 3s2, 3p1. That's aluminum, okay? That's the ending electronic configuration. There's 2 electrons in the s, 1, 2 plus 1 equals 3, that's the number of electrons. 2 of them together. So when you did the boxes, up, down, you had 2 together, 1 apart. 2 together, 1 apart.
Oh, okay.
So it's not 1, 1, 1.
So what it is 1, 2, 3, 4, 5, 6, 7, 8. To make a long story short.
Yeah.
But it's based on this because remember the electrons don't fill up, they don't pair up till they have to.
Oh, so you pretend like the top is the S
Yeah.
orbital, and then the rest are the P, and you've got to go in order based on up, down, up, down, up, down.
Right. But they don't pair up till they have to, punch
Right.
rule.
Right.
The next one would go here. The next one would go here. Because they're electrons, they repel each other, they don't pair up till they have to. So if you had, this would be phosphorus. Phosphorus is 2 on top. It would be 3 apart. 2 together, 3 apart. That's why it's like that.
Okay.
Okay.
Oh, now I see what your question was. With the dots.
With the dots. It's tied right into the dots. Okay?
Yeah.
They don't, electron is an arrow. They don't pair up till they have to because they're negatives. But what they do is that one has a clockwise spin and one has a counterclockwise spin. Did I do this for you guys yet? One has a clockwise spin, one has a counterclockwise spin, so they have opposite spins. One is pointing up and one is pointing down because they have opposite spins. Extra credit next week is to be able to do this.
How many
Never.
points extra? I'll practice all week.
Don't do that. Study this. I'm joking. I'm joking. The AP psychology teacher always wants me to come in and do this, but I've just been doing this for years. I was getting observed here at HCC by the department head. We have a new department head now, but the old department head, I was getting observed. And I was teaching that. I was going like this. 5 minutes later, I looked back at her, Dr. Pison, and she's like, I get that out of a lot of students too. So opposite spins, you gotta have opposite spins, okay? All right. Also, silicon here has a dot in it.
As a what?
See that I there?
A tittle?
Whoa. Yeah.
Just saying.
On top of an I or a J, it actually has a name. It was also a question in the big tournament in Thermon. I don't know if you remember.
Oh, yeah, it was. We got it because I knew that.
I knew that too. What I do
No,
is whenever you have an I in there, is I make them Lewis X's. You can make Lewis dots, Lewis X's, Lewis hearts if you want. It doesn't matter to me. But I kind of, when I got that I in it, I make something else. You are right. It's called
Boom.
two. Okay? And argon, 2 on a side. All right, you know how to do this. However, it's not going to matter once you start putting it together. You're going to see here in just a second. Those are Lewis dots.
And it goes clockwise?
I go clockwise.
Cool.
Okay. All right. Ionic bonds.
Yes, please.
All right. Sodium chloride, for example. Sodium's got 1 dot. Chlorine's got 7 dots. The magic number is 8. Transfer of electrons. Sodium likes to give up that electron. Chlorine wants to gain it. Once this loses it, so this 1 electron is transferred from sodium to chlorine. And you have to think of it, it's not totally true, but you have to think of it as it gives it up and it doesn't give it back. All right? So, when that happens, now chlorine gets an extra electron, it's negative. Sodium lost an electron. Okay? It's positive. It forms ions. Ionic, get it? All right? So that's where you get an ionic bond. It's usually a metal with a non-metal. Usually. really far apart, metals and nonmetals, sodium chloride, or the farther apart on the chart, the more ionic it tends to be. Okay. There's a way to tell. Did you do any exercise where you had to subtract electronegativities to see what % ionic or covalent something is?
No.
There were videos.
There were videos?
Yeah.
Okay, but to make a long story short, the further apart they are, the more ionic they're going to be. And the closer together they are, CC, close covalent, the closer together they are, the more covalent they're going to be. Yes?
A metal and a non-metal are never covalent, correct?
No, because what happens is you can calculate the percentages. You take the electronegativities and you might get, I don't know what it is, 75% ionic. That means it's 25% covalent, which means it's not totally giving up the electron.
I'm confused by the terminology for ionic and covalent.
Well, think of ionic as giving it up and then one of them taking it and never gives it back. Think of it that way. Whereas covalent is going to share. There's going to be a little tug of war between them, and one of them doesn't get to hold on to it totally. That's what. And all this homework is covalent. All of this experiment 12 is all covalent. Okay. All right. Now, covalent, co together with, like co-champion. Carbon dioxide, your example. Notice carbon dioxide real close together on the chart. All right. Now, I like to differentiate. Okay. Your book may or may not do that. I like to do this in the beginning, but I like to differentiate between the two. I make one of them, like sodium, I'll make an X, and then I'll make these, and so you can just kind of tell them apart. It's not really super important. When you get good at it, you don't have to do it. But in the beginning, you might want to do it so you can say these are from this one and these are from this one. Okay, so this one's transferred. It makes a strong bond. It won't let go. X is enough. All right? Now, carbon dioxide. Anybody?
3, 4.
What's that?
Sorry, 4.
Carbon is 4. Okay? And you're going to ask me, where do they go? And it's kind of a guess and test kind of thing. I like to work outside in. For 1 second, put your pencils down and just watch me. Just watch. I like to work outside in. And when I say outside, oxygen's got 6. See how I'm going the outside? Carbon's got 4. What's the magic number?
8.
8. And when in the beginning, you might want to circle these. Are the oxygens good?
Yes.
But I only got 4 around carbon. And don't do this. Don't make a circle and then go over here and get it. Don't do that. All right? Don't do that.
Do what?
I'm going to move 2. And as long as these 2 are beside the oxygen, they're good. And I'm going to move these 2. It doesn't matter which 2, they're all equivalent. Now, you got the magic number? That's this whole lab.
So our book says to, whenever you're drawing like the Lewis structures, to go ahead and put 2 in between each one. So like.
Yes, to start with. You know you've got to have at least 1
Yeah.
bond, so you put 2 to start with. I'm going to tell you something right now. I've been teaching this wrong for 40 years. And I didn't realize it until I started teaching here that I really do it backwards. I work outside in. The books work inside out. If it makes sense to you, if you learned in high school or something, inside out, go with it, do it, you'll get the answer. We'll both get there the same way. I like doing it this way. I like going outside in. So, whichever way makes sense to you.
Well, yesterday I was watching a video on YouTube, and then the way the lady was doing it is that carbon is 4 electrons, and then she multiplies 6 times 12, which is 12, plus 4 is 16, so.
Yeah, she has to get the total.
Right.
You want to get the total
I saw that.
electrons to start with, which is, yeah, we're going to do that. That's it. This column right here, number of electrons you want to
Yeah,
count.
and then like if you put 2, and then like you already used 4, so then like you need to figure out like the 12 on like the outside.
Yeah. Okay. I'll get to that in a second. All right. I'll come back. I just wanted to explain covalent bonds. Covalent, in the intersection of the circle, do you remember Venn diagrams?
Mm-hmm.
In the intersection of the circle, you have shared electrons. There's a tug of war between them. you don't get the big positive, big negative out of this. You get a tug of war between the electrons, and one of them's not winning nearly as much. All right? So, this one transfers, this one shares. Everything we're doing over here is sharing, is this kind. Usually it's two nonmetals. We'll do more examples of this in a second. Okay? All right. Single bonds. All right. So, carbon, for example,
That's not us.
this is carbon. Two together, two apart. But when I do CH4, right? I'm going to have 4 apart, right, to get that one to work.
Yeah.
Yeah.
So, yeah, if carbon's by itself, but when you start bonding it with something, those electrons can move around. Okay, so, I want a different color here. All right, so, when you're doing this is an example of a single bond, all right? Now, thank you. Let me do it again, did you get it?
Wait.
Single bond.
Oh, single ladies.
Okay? I work, well, first of all, carbon's got 4, hydrogen's got 1, times 4, total of 8 electrons, all right? Your picture has to have 8. Don't know how many times I had a student bring me a paper, what's wrong? They count the electrons and they pull 2 out of the air, they missed it. They don't have the right number of electrons. You've got to have the right number of electrons. So your first,
Can't they just say it's ionic and shove it away?
no, this one's not iron. You have to think of hydrogen as being a non-metal, by the way.
Oh, right.
You have to think of hydrogen as a non-metal. This is going to be very covalent. All this is going to be covalent. All right, so hydrogen has 1. We make X's and O's, it doesn't. The magic number is 8, except for hydrogen. Hydrogen's got 1, needs 1. The first shell only holds 2 electrons, so hydrogen's always going to be an X and an O, right? But everything else is going to be 8, is the magic number. In the beginning, you might want to circle these. All right? Okay.
Why
Carbon-
does hydrogen want 2?
It's got 1 and it needs 1 to get 2. First shell only holds 2 electrons.
Because it's trying to be the closest noble gas, which would be helium.
Helium, yeah.
Okay.
But everything else is 8. The magic number is 8.
Okay.
Octet rule, did you do the octet rule somewhere?
Yes.
Somewhere along the line. Octet rule. I think octet rule was on Jeopardy this week. Oh, I gotta ask you about the Jeopardy question later. Okay.
Fine.
All right. Now see, in the intersection of the circle, there is 1 pair of shared electrons. That means that that's a single bond. All right? So everything's got to have at least a single bond, right? So at least it's going to start with 2 electrons, right? You put 2 electrons in there. Don't think, also, don't think that every bond has to be an X and an O, because it doesn't. Okay? It doesn't. Don't forget to, Shauna, don't forget to sign it.
It's somewhere. I don't know.
That's a single bond, all right? Oxygen. Yes, very green. Oxygen's got, count the group, it's got 6 times 2.
4.
I work outside E. Got 6. And notice I'm going around the outside too. It needs 2 more, right? This oxygen is good, but this one only has 6. And don't do this. Don't make a circle and then go over here and get these 2. And don't do that. If you want to circle it, put it in between. If you don't want to circle it, don't put it in between. In the intersection of the circle, there is 2 pairs of shared electrons. That's a double bond, just like this. Those are both double bonds. They're 2 pairs of shared electrons. Oxygen, O2, double bond, just double line. But you want to include all of these loose electrons here, okay? That's the complete drawing.
So they don't go singularly.
Technically they do, but it's beyond the, you need to know molecular orbital theory to do that, and we're not doing that.
No,
That's
thanks.
basic.
Sounds like I don't want to.
I'm 2 weeks away from being done with this.
They technically are. Oxygen is, pure oxygen, liquid oxygen is blue in color, which again,
Oh.
I think was another Jeopardy question this week. Triple bond, nitrogen. Nitrogen's got 5.
5.
All right, you're not going to do this unless you get a triple bond. I'm going to have 3 on side. In the intersection of the circle, I have 3 pairs of shared electrons. That's a triple bond, and the triple bond is going to look like this. 3 lines. And get those loose electrons in there. Okay? I would accept either one of these. This is a Lewis structure, that's a structural formula, but I would accept either, and the AP exam does the same thing. They accept either one of those as being correct for a Lewis,
Us too.
Lewis dot structure or structural formula. They'll take either one of those. Whenever I give quizzes on this, I make them do both. I make them.
Well, now, you don't need to do that.
Mm-mm.
But your lab only has room for like the Lewis dot there at the beginning. Okay. So far so good?
No.
Could you try and do so like the way without the X's? So like the way that like doing it so like because we learned it well I don't want to speak for like everybody but like if you're reading the textbook and you're learning from the textbook when we're looking at that I'm literally lost. Could you do it from inside out versus out or whatever you
I'll try.
the opposite?
Your X's and O's are a dash in the textbook as a double bond, and they just count them as 2.
Right.
I think
Okay.
that-
And I'm showing you how to get there, because when you're doing the dots and everything, then if I got 2 pairs in, oh, that's a double bond, I redraw it.
Yeah.
But I will accept on the lab that first thing right there. I would accept. Okay, let's do water.
I'm not understanding why that's a triple bond and not a double bond with the electrons like just evenly placed around it.
Well, it's a triple bond because in the intersection of the circle, there's 3 pairs of shared electrons. 2 pair here, 1 pair here.
So like you're asking why it's not
Like a double bond and then the other 2 electrons go on top and on the
like
bottom.
or even like a single bond.
Yeah.
No, because that's what happens here. This total electrons here is 12. Here, the total electrons is 10. So it has to do with the number of total electrons in the picture. Okay, let's do water. Add up. First of all, how many electrons?
8.
Oxygen's got 6. Hydrogen's got 1. And there's 2 of them, so a total of 8. All right, so you get 8. Lewis structure. Generally, the first one is not in the middle. In this case, H can't be in the middle. H will never have a double or triple bond. H will never be in the middle and have a bond going to either side. H is always just a single bond. All right. So H O H. Now, you want to do. Well, you know you got to have at least 1 bond, right?
Yeah, because you
Right.
go ahead and put the
So, and hydrogen's always going to be XO. Got 1, need 1. Got 1, need 1, right? Oxygen has used 2. I have 4 left over, right? And they tend to jump around in pairs. So, I got 2 there, I got 2 there. Better or worse? I call this bonded pair. They call it bonded groups. All right. You need page, is it 95 and 96? Page 95 and 96 out. You need page 95 and 96 out.
It's not us.
Thank goodness. You need to have that. There are 6. All right. This.
Oh, I already had that.
Yeah. So the first one's a linear molecule, right? On page, it's a linear molecule of some sort, linear line straight across. This bond angle is 180. This one's 180. It's basically 360 divided by 2. Okay. So linear looks kind of like that. Trigonal planar, the next one. Trigonal tri 3. Planar, flat, lies in one plane. Ends in AR. I thought it would end in, I put ER for years and years and years, but it ends in AR. Is it AR in your book?
Yep.
Yeah. I need ER. Trigonal planar, 3 things. Try to spread out as far as possible. So all the bond angles are 360 divided by 3, 120. You're going to have to know the bond angles too. Now, 4 things in space. You would think the bond angles would be 90 degrees, but it's not. It's a tetrahedral. Tetra means 4. Everybody, once you do the naming compounds, you learn tetra is 4. They tend to remember 4 is tetra. Okay? Tetra, I had a geology professor call this, no matter how you drop it, 3 down, 1 straight up. The bond angle is 109.5. It's an odd number. You just got to memorize it. Okay? So that's a tetrahedral. The next one, this is ammonia. Trigonal pyramidal. I call this one tripod. This is tripod. This, 3 of them pointing down, nothing up top to balance out the picture. This is asymmetrical. Okay, 3 down, 1 up. All right, and then the last one is bent. I've seen V-shaped, I've seen angular, I like bent, I can spell bent. All right, I call that, and that's water. Water is a bent molecule. All right, so how do they get this? Water is half a tetrahedral. Okay, water is half a tetrahedral. So, how many bonded pairs?
2.
How many lone pairs?
2.
Today's vocab word. Lone. Take out the L, you got 1. Lone, as in alone, or somebody who has no friends. A loner.
It's me.
Do not spell it L-O-A-N, I think you get from a bank, which I've seen way too much. Okay? Alone. They're lone pairs. I've had students call them loose pairs, and I kind of like that because it's these ones here. They're not in the intersection of the circle. They're ones on the outside. So they're lone pairs or wait. Ignore what I just said. They have to be on the central atom. Okay? But loose pairs. Lone. Io silver.
Away. Lone Ranger.
Lone Ranger. Texas.
Roadhouse.
The Lone Star State. There's only one star on their flag. Lone Star State. Lone. All right, 2 and 2. So you look on the paper. 2 and 2 is. It's 4. Okay, I'm going to come to this. There's a blank there on your paper. I want you to add polar or nonpolar. It's an overall polarity that's really kind of big. I don't know why they don't have it there. All right. So what's the shape?
Bent.
So it's bent, right?
But it's a
Okay. So what happens is molecular geometry, 2 and 2 is bent. That's the molecular geometry. You add it up to 4. And what's the one that adds up to 4?
Tetrahedral.
Tetrahedral. In other words, see this one? That's tetrahedral. This is 3/4 a tetrahedral. This is half a tetrahedral. So what they're trying to do, what they're saying there with the electron geometry is it's everything bonded pair plus lone pair. They're adding it together. So this is tetrahedron or tetrahedral. I've seen both. I would take either. All right. Bond angle. What's the bond angle say?
109.5.
It's a little less than 109.5.
It does
Oh, it
say
does,
less
yeah,
than.
it does, yeah.
Okay.
Oh, it says less than, yeah.
It's actually 105, 104.47. So is that
Do we
less
have
than?
to memorize that?
You got to do just the 105. What's just the 105?
Okay.
You don't
So
have
I'm
to do
like,
that.
how do you
What happens is,
know?
if you have a lone pair, and they're sometimes called loose pairs, they take up more room. And when they take up more room, they push down and make this bond angle just a little smaller. So because they're loose and they're not tied together, tied into a bond. All right, bond polarity. You want to do a couple more examples first, and I go back and do that.
No, what is it?
Bond polarity.
So that's just So on our lab sheet, it's the other way. It does not matter how you write
Is
it.
it pointing toward the oxygen?
O
Yeah.
is first. It's
It's
pointing
O is
towards
first,
the
and then
As
oxygen.
long as it's pointing toward the oxygen.
Yeah.
It's got to
Okay.
point toward the oxygen.
With like a plus line.
Okay, with that, it's a little delta, that's a small delta, little delta positive. And what happens is, you get big positives, negatives here with the ionic, but you get these little positives and little negatives with the covalent, and they use the little symbol delta, small delta. There's a slight positive and negative in it. Okay. Do you have a table of electronegativities? You need that, you don't, technically you don't need it. You have that? What element has the highest electronegativity? Fluorine, and what is it?
4.
Fluorine is 4, FF. Fluorine is 4, it's alliteration. Did we talk about the Urbana bananas?
Yeah.
Yes.
I made that up. Savannah, minor league baseball, Savannah bananas. I'm not making that up. That's real. That's real. I agree. All right, fluorine. Okay. So what's electronegativity? Electronegativity is the tendency to attract shared electrons. Electronegativity is the measurement of the tug of war between these electrons. Now, if you have the same element, right? They have the same electronegativity. Nobody's going to win that one. You're not going to have an arrow. You'll just have and don't put an arrow. Remember ionization energy? Do you remember ionization energy? Ionization energy is talking about one atom, one electron. How much energy does it take to take one away? Did you do electron affinity? Okay, it's just the opposite. It's gaining electron. Okay, you don't. Whereas electronegativity, the difference is you're talking about two atoms, the electrons in between, and the tug of war between them. Okay, but who wins that? It's not the big atoms; it's the small ones. And fluorine has 7 valence electrons, and it wants one. It wants it really wants it. You will not find fluorine in nature. It's too reactive. It wants to gain an electron too much. So fluorine is very reactive. So fluorine's the highest. So what is it? It decreases this way. It decreases this way. Okay. Snowman or inverse snowman?
Inverse snowman.
It's an inverse snowman. Okay. So it's an inverse snowman. So it does this, and then
And
okay,
it falls over on its head, but that way.
which is I showed the picture, right?
Yes.
Okay.
The little baby inverse snowman.
And the inverse snowman. That used to be a snow day assignment. So all you're doing is you're going to pick and point an arrow toward the one with the higher electronegativity. Now, that's all you got to do. And you can have a chart. You'll be allowed to have a chart. Bring all of that next week for your final next week.
Oh God, I forgot I'm gonna panic. Throw up. I'm sorry.
Anyway.
The dramatics, I know.
Okay.
I drew a vomit face on our last exam.
All right.
That was bad.
Yeah. Just always point it to one. with the higher, you get all those papers, bring those next week. We're gonna do it, what room was that, 203? We'll do it in the same room.
Okay.
Bring it back.
Bree, did you hear that?
You know my shit? Hey, I got a great grade with your calculators. So.
Okay. All right. So, what else was I gonna say about this?
Is there an extra credit assignment for this one?
No, I don't have one.
Come on.
Backwards.
You can do the same one, and then just
No.
let me get it right this time.
Can I make you a
No.
inverse snowman on a dirt or something?
No. Okay. Now, this is an overall polarity. Okay. This is overall polarity. I'll get to that in a second. This arrow is a vector. Vector is a physics thing. Did they talk about the vectors?
Yeah.
Okay.
They just had it in like parentheses and put vector.
Okay. Here's a long story short. Vectors have magnitude and direction. What happens is the wind, 10 miles an hour out of the north. You're in your car on Interstate 70 going 55 miles an hour west. It's got a number and it's got direction. All right? Scalar is the opposite. You don't know this word, but temperature, 22 degrees, doesn't have direction. That's scalar. Vectors have magnitude and direction. Okay? At this point, oh yeah, I would show you a video explaining vectors that have magnitude and direction. Has anybody seen Despicable Me?
Yeah.
There's a vector in it. And he says that he has magnitude and direction. He actually says that. Okay. So, if you have a molecule like this, okay, carbon has a higher electronegativity, right? Carbon's higher, right? 2.5.
Yeah.
2.5. So look, everything's pointing. Oops. Everything. They're all going toward the same. Now there's this thing called vector addition, and you add vectors head to tail. And this one, you have to think of it as kind of a. Does it come back to the starting point? Yeah, nonpolar. Water is bent. Water pointed toward the. When you add the vectors, you pick them up. You cannot change the length. You cannot change the direction, but you add them head to tail. And so when you add them, see what you get? Does it come back to the starting point? No, and it's polar. You can have things that are slightly polar where they almost come back to the starting point, right? Linear. You got this, you got this, right? Add them together, it's simply going to be this, back to here, come back to the starting point, not polar. Now, I can give you the
Wait, they
answer.
come back to the starting point and they're non-polar?
They're non-polar.
Okay.
Okay. So what happens with water? Water is a polar molecule because it's got a positive end and a negative end. Polar, North Pole, South Pole. Polar is asymmetrical. Symmetrical is nonpolar. Everybody hates those definitions because the uns and nons don't go together.
Mm-hmm.
It seems backwards, I know. So if it doesn't come back to the starting point, it's polar. Very polar. Water is very, very polar. It's a big deal. If you don't learn anything else in this class, water is polar. And it's a big deal somewhere in. Did he talk about hydrogen bonding? No? Okay, never mind. If you start talking about hydrogen bonding in biology classes or anything, it's because water is polar. It's got a positive end and a negative end. Okay? So in that one blank one, give me an overall polarity. This one is bond polarity. Okay? Just the bond. Can you have polar bonds and then an overall nonpolar molecule? Yeah. Right here. You got polar bonds, but you got an overall nonpolar molecule. Let's try the next one. What's the next one?
CS, CS2.
CH4?
CH4.
Well, you basically.
CS.
Okay, do I need to do CH4?
Yeah.
I mean, that's what y'all say.
Is the next one CS2?
Yeah.
Yeah.
I mean, you can keep going with the CH4 just to do like the
All right.
geometry and stuff.
Generally, the one that's written first is in the middle. Did you add it up? 4, I already added it up. It's 8. How many bonded pair? 4. How many lone pairs? You're only counting the central atom. When you're doing bond pair and lone pairs, you're only counting the central atom. For example, if you're doing carbon dioxide here, you would not count these out here on the oxygen. You wouldn't count those. You're only counting the central atom. 4 and 0. For a total of 4. Which makes it a
Tetra.
tetrahedral, which makes it a, they're both tetrahedral, because 4, anytime this ends in 4, these two answers are going to be the same. Sorry, not 4, 0. Anytime this ends in 0, these two answers are going to be the same.
Okay.
Okay, bond angle, 109.5. Give me a degrees on there. And which one's it? 0.2. Carbon. Hydrogen, you got to kind of. Hydrogen is 2.2. 2.2. 2.1. Okay, you ready for CS2? CS2. All right. Carbon's in the middle. All right. How many electrons total? 16. Right. Carbon's got 4, sulfur's got 6 times 2, 12 plus 4, 16. All right. Do you want to watch me do it, or you want to?
Okay, I try.
You want to try?
Try.
Okay, I'll give you a second. You can try. Well,
But then on that
no, no.
chart, it says tetrahedral, you know,
No,
the
no.
two together,
This is linear. This is linear.
This one.
This is linear.
Well, that's not what he says in the
Yeah,
video.
yeah.
Okay.
It's because the carbon has 2 things attached to it.
Okay.
And it doesn't matter whether it's single double or triple. It's got 2 things attached to it, 2 and 9.
Okay.
Don't double that.
Okay.
But it's good to know that carbon always has 4 bonds. That's a really good thing to know, that carbon always has 4 bonds.
I have a question. I don't understand this one.
Lone pair. This one doesn't have any lone pairs. This one has 2 lone pairs right here and here, the top. There's lone pairs, there's nothing bonded to it. There's nothing bonded to it. See here? I got electrons here, right here, but there's nothing bonded to it. That H is for them.
Okay.
And they have to be the central atom. It has to be the central atom. Okay. So carbon's got 4. You want to start in the middle? Sulfur's got?
5.
You need a pencil and an eraser to do this, because it's just big time guess and test. Everybody keeps asking me, how do I know where to put them? And the answer is you don't. You got to move them around. You have to erase, pencil and eraser. Put them someplace. It works great. If it doesn't, move them around. So, sulfur needs.
2 more.
It's got 6, right?
Yeah.
And if I circled right now, the sulfurs would be good, right? But carbon only has 4 around it, so I got to move 2. It doesn't matter which 2, they are equivalent.
See, I find it easier to draw the line bonds first.
Okay, well then do it that way.
Okay.
Yeah.
Do whatever makes sense to you.
Okay.
I'm not used to having people that have like prepared for class that have like looked at videos. I'm not used to that. Like,
Welcome.
like it. meet me halfway, kind of.
Yeah.
So if we were writing with like the lines for the bonds, it would be like S and then a double bond C, double bond S, and then there's
Yeah, I want, yeah, uh-huh. I will accept this, but it also has to have those dots.
yeah. Doesn't matter where the dots are.
I would take this drawing or this drawing, does not matter. Does it matter where these go?
Oh, okay.
No.
Okay.
There is a way, we do it in AP. We're not messing with this. We do that in AP. Okay. So, how many, and there's a trick question here, how many bonded pairs?
4?
No.
Oh.
2. The carbon has 2 things attached to it. Don't double it because they're double bonds. The carbon has 2 things attached to it. Okay? So it's 2. How many lone pairs? The lone pairs would be here or here. Any lone pairs?
Question. The carbon has 2 things attached to it because it has 2 sulfurs attached to it?
Right, 2
Okay.
sulfurs.
Okay.
So single, double, triple just all count as one thing.
Gotcha.
Yeah, see, a lot of times you can get this bonded pair, 2, 4, 2. A lot of times you can get that before you even do it. You don't even have to do it to get that, but you have to do it to get the lone pairs.
Mm-hmm.
But the beginning, yeah.
So on the bottom, the lone pairs would be in the middle, on, like if there's nothing on the C.
If there's nothing on the C,
It's
that's
just a
0.
lone pair, okay.
They got to be on the central atom. The lone pairs have to be on the central atom if you're counting. This is all based on the central atom because everything kind of spokes out from the central atom.
Thanks. Can't wait a minute. There's gonna be like one question on the test for this.
No.
right?
There's going to be a preponderance. Yes.
Maybe just one.
No, there's-
And I hope
it's
that
already made up.
H2O.
It's already made up and it's already printed out. So,
So did we get a copy of that today?
but
Give us a copy.
no, I don't have the copies yet. I don't have the copies yet. They're printed off.
It's fine, you can share that with us.
Okay, 2 and 0 for a total of 2. Polar or non-polar? Non-polar. By the way, look, is this the same as this? Carbon dioxide and carbon sulfide, or it's the same? Because oxygen and sulfur are in the same group, right? If they're in the same group, you're going to get the same thing because they got the same number of valence electrons. You're going to get the same answer. So I could make up lots of different and answer lots of different questions, but there are only a finite number of things can be because a bunch of them are going to be the same. All right, non-polar. What is it? 2 and 0. On the paper, 2 and 0.
Oh, the linear one.
Linear. Liner. Liner. Remember, I said whenever this ends in an O, these 2 answers are going to be the same. All right, bond angle.
180?
Yeah. And
Carbon to sulfur?
which one?
I thought it was
Carbon's higher. What's sulfur?
They're both
They
the
don't
same.
say 2.5.
Oh, it's a tie?
But yeah.
Just a double one.
So if it's a tie, and they're both 2.5, although there's a little bit of different size of atoms, there's going to be a little bit of something else. Just put a line. Don't put an arrow, because one of them is not pulling the electrons more than the other one.
Wait, they're both 2.5? What is that? I don't understand.
Or the electronic.
Negativity.
Oh,
Okay.
yeah, I left my whole freaking thing
Yeah.
at home. Oh, have to. Can I take a picture of that?
Yeah.
Thank you.
Okay, let's do something here real quick. While I'm thinking of it. All right.
I was just gonna ask you to do an example of the polyatomic.
Yes, I need to do that. All right, linear. This is not cut and dry. Linear. Polar or non-polar? You can put this on your paper on page 95. Linear, polar or non-polar?
Non-polar.
Non-polar. Symmetrical. Trigonal planar.
Trig? That'd be
Trigonal
polar.
planar.
That'd be polar.
Non-polar.
No? Oh,
All the bond angles are the same, right? You got 3 things spread out evenly in space, right? They all want to spread out. This is called Vesper. Do you have the word Vesper? Vesper.
Like a Vespa?
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 What's that?
It's in this week's.
Okay, that stands for, by the way. Okay. This is called Vesper theory. Valence shell electron pair repulsion. So valence shell electrons, right?
Oh.
We're doing the valence shell electron. Pair repulsion. They're trying to spread out as far as possible. Things want to spread out as far as possible. Trigonal planar, you got three things, they spread out evenly. Each bond angle is equal, 120, 120, 120. Polar or nonpolar?
Nonpolar.
Nonpolar. What's the next thing?
The tetra. Oh, bent.
There's a bent down there. Both bents,
There's both, yeah, there's two bends.
there's two bents, but both bents are polars. One of them's 2 and 1, and one of them's 2 and 2. All right, tetrahedral,
Well, nonpolar.
nonpolar.
And yeah.
Is that what it is? You said tetrahedral nonpolar?
Nonpolar. What's the next one? Trigonal pyramidal.
Wait.
Pyramid.
So bent is polar?
Bent is polar.
Okay.
Polar. Trigonal pyramidal is polar. It's asymmetrical. See, it's got three things pointing down. It doesn't have anything pointing up to balance out the picture, right?
I just go up like this if there's any lone pairs on the center item.
And the last one is bent is polar. Yes. So what happens, and this is not 100%, but if it's got 0 lone pairs, it's nonpolar, and if it's got lone pairs, it's polar for the most part, yeah. When in doubt, that would be a good guess. Okay. Anybody still got heat out off their, okay. What the, all right, now, I'm gonna give you a curveball. If I've got CH4, and I take one of the H's off and put a Cl, if I take off one of the H's and I put on a Cl, which are normally green, have I messed up the symmetry? Can you mess up the symmetry? Yeah, so don't think that tetrahedral is going to be 100% nonpolar. They could take off one of the things, put something different on there, and it messes up your symmetry a little bit, because what happens, one of the vectors is a little longer and it won't come back to the starting point. So that's a curveball that you may have in there someplace. All right. You need to write this down too. Why do we have to learn polar and nonpolar? Why is polar and nonpolar such a big thing?
Why?
Because polar and nonpolar don't mix. Oil and water. Salad dressing, shake it up, separates into layers. Polar and
vinegar.
nonpolar don't mix.
Oil and vinegar.
Right.
Okay.
Salad dressing, shake it up.
So good.
I used to do a demo where I take styrofoam and drop it into acetone, and the acetone would dissolve it.
Mm-hmm. That'd be fun.
Yes, so you gotta, somebody was trying to hoard gasoline, and they were getting they went to Walmart and
yeah.
got one of those big rubbery things. Gasoline's gonna eat through that.
Learned that from Breaking Bad.
That's a good show.
Hydrofluoric acid.
Hydrofluoric acid. Yes, I was
Hydrofluoric.
trying to think of the acid.
I know. I tell my
Hydrofluoric.
kids all the time how to hide bodies. Oops.
Yes, hydrofluoric.
I'm not kidding. I do tell them.
What household chemical is a really large molecule, has a polar end, has a non-polar end, dissolves in both polar stuff and non-polar stuff?
Baking soda.
No.
Bleach.
What?
Bleach.
No.
Laundry detergent.
Boom.
That's not real.
Is that why it cleans
So-
things so well?
That's why you use it to clean things, because soap or detergent, any of that, it's a really large molecule, C17H35. It has a polar end and a non-polar end. It makes a little micelle. You might have seen that in a biology thing. It dissolves in both polar stuff and non-polar stuff. That's a big thing. I had it last class I had last semester. There was somebody who was making soap. She knew that right away because that was her little business to make soap. So she knew that answer right away.
Nice.
All right. Now, Can I erase this?
Hard flex.
Bree, pick one out. A polyatomic, one with a
Okay,
ClO3. Don't you have CL?
SO3.
SO3? Does it have a charge?
Yep,
Negative
-2.
two.
Could have done one with 3, and then what do we
But
do
that's
with
not
the arrow?
polyatomic.
But I did.
That's a
want to know about
polyatomic.
those
That's
two.
sulfite.
Oh, no. I was
That
talking
was-
to her. That's a polyatomic.
She's talking about something else. I just want to know when those 3 elements, how you do the line.
Okay, I'll come back and do that one next.
That's 6. Okay.
Okay. All right, sulfur has 6, oxygen, 6 times 3, plus 2.
Yeah.
See that -2? Electrons are negative. You add 2 more electrons to your picture. Today's word, counterintuitive. If it's negative, you add electrons. If it's positive, you take electrons away. If it's +1, you take 1 away. So what's that add up to? 18, 20?
26.
26, okay. So this adds up to 26 electrons. Sulfur's in the middle, oxygen, oxygen, oxygen. It does not matter whether you go side, side, top, side, side, bottom, top, bottom, side. Don't get hung up on it. If your picture, I can sit there and rotate it and get what you got, or I could flip it like a mirror image and I got what you got, that's fine. All right, don't get hung up on it. Give it a try. Go ahead. Give it a try. Give me a pencil and an eraser. I'm going to collect. Yeah. Yeah. That hardens up after. Oh, wow.
They had those little bodies on the show in Ohio, and they had the, like, the really, like, the big ones that you
Yeah.
could, like, put around your neck, and I was like, this is fancy.
You
But
should
they were
really
just-
saw it.
Yeah.
Okay, so
Yeah, it's Did I get yours?
no, I'm trying to steal it from you.
Today's word, filter.
Pilfer. Pilfer first, or pillage first, burn later.
These things, they'll last. They're reusable, but if they get a crack in or hole in them or anything, they're not good anymore. So.
They're not cheap.
Okay, I got 3 that haven't been clicked.
Is one the clear bag? Oh, the clear bag is so cool.
I only have one of those left. I used to have a bunch of those.
Okay.
I want to record it. I didn't get a chance to record it from the beginning. For Katie.
For Katie.
For Katie.
I need those in my booster.
They're warmer than a
Yeah.
They're way more
Yeah.
than a hand warmer.
They had,
That
like,
one
big
got
ones.
really cold.
They had big ones at the
Heat and a
so
clip.
they were like this big. I was like, I need
Okay,
Yes, for real.
that.
which way do you like better? Inside out, outside in?
Inside out.
So you're going to have to, and if you do it this way, I can't differentiate between the oxygen and sulfurs, I don't think. Did you do that to start? Sulfur's got 6?
I did lines between all of
Yeah,
them,
I just
and
did
there
that.
was going to be one bond at least,
Okay.
and then I tried a double bond and it didn't work, so I knew it was just a single bond to each.
Okay, so sulfur's got 6.
Right.
I've used 1, right?
Oh wait.
Or did I use, see, I can't tell. Okay, now what?
You used 3.
So you use
I got
you
6
said
left
6 of
over?
them. So
Use
just
6.
fill them all, or try. So that is 2.
And now you need 2 more.
Okay.
So then you'll have to erase one and put a double bond.
Anywhere, it doesn't matter, they're all equivalent.
Right.
One double bond?
Just
Can-
one.
Yeah, one double bond. Right?
Screw me.
Is that right?
Okay.
Now, let me add one thing. Whenever it's an ion, you put it in brackets,
Oh yeah.
and you put a charge around it. to show that it's an ion. Positive or negative, either one. You gotta show it.
-2.
Okay? So you have to, in your head, you have to realize that a double bond is 4 or 2 pair electrons.
So you don't have to have a, if a double bond goes to one atom, it doesn't have to go to all of them.
No.
Okay.
And again, that's something people think at the beginning, that if you got all singles or all doubles or whatever, it doesn't. Doesn't have to have that.
So what would be the bonding group? Would it be 4?
No. 1, 2, 3. Right? Remember how I told you to get it before you even did it?
So
3.
why wouldn't you just put 2 atoms below the sulfur? Oh, because it's attached to the oxygen. Wait. No, that doesn't matter because it's the whole ion is -2. Why wouldn't you just put 2 atoms below and make it 3 single?
That's because that would be take 28 electrons. You can't do it. You don't have enough electrons.
Okay.
You would need 28 electrons to get that.
I see.
All right, bonded pair 3. And I know that's a double, but it only counts once. 3 things attached to it. How many lone pairs? And the lone pairs would be
0.
right there. 0, 3, and 0.
3.
For a total of 3, which is trigonal. Planar. AR. And I said when that's 0, the 2 answers are the same, right? Trigonal. Planar. What's next? Oh, I forgot polar or nonpolar. Is it polar or nonpolar? Nonpolar, yeah. It's trigonal planar, it's nonpolar. Bond angle, 120. Degrees, don't forget the degrees. And I got sulfur and I got oxygen. Which one has a higher electronegativity?
Oxygen.
So I'm going to point the arrow toward oxygen. Starting to make more sense? You got to do it. It's like anything else. You got to do a bunch of practice. And if worse comes to worse, you can just Google what the molecular geometry of something.
Blessed.
You want me to do one?
Yes, I wanted you to do one that had 3.
Okay.
So like C2H2 Cl2.
Yeah.
Yeah.
Or that one.
Or yeah, whatever.
If they write HCN,
Yeah.
don't juggle it. Just put H, C, N. They're trying to tell you the order.
Oh.
Okay.
Okay?
Is that the same with C2H2Cl? So like it would be.
Give it to me again.
I'm sorry.
C2.
H2Cl2.
Okay.
So.
H's are never in the middle.
Yeah.
All right. So this one is C and C are bonded together. All right. And then the H's and the CLs, they have a question here. Or go off like that. And that's
Why?
I'm not telling you the bonding.
No, that's okay. But bond polarity didn't. How do you do the arrows in it? There's 3. Like you just rank them.
Oh, true. That was
Okay.
That's what I mean.
If you're doing, yeah. What's that? Okay. Pretend the green are chlorine. Okay. If I had it like this, now these are hydrogens. Chlorine and hydrogen have different electronegativities. Okay. So my arrows for these, if I've got it drawn like this, my arrows, the big ones, be like this, and then I'd have little ones like this. But when I added those 2 together, they'd cancel out. When I added these 2 together, it would cancel out.
So nonpolar.
And if you drew it like this, it would be nonpolar. Okay? This has a special name. I don't think you have to know this, but I'm going to tell you. When they're across from each other, you know what word you use? Trans. Okay? Because they're across. Transcontinental Railroad. Right? But if I do this, and you have a question about this at the end. Now, is that polar or nonpolar?
Nonpolar.
These vectors are going to be smaller than these vectors. They're not going to cancel out this way.
See, I always just go by the lone pairs, so.
No, well, see, this one doesn't have any lone pairs, so you can't do it totally
Yeah.
like that. You have to be able to picture it. This is polar, okay? Oops, I did it. And there's one more way to do this, which is actually different.
How are we supposed to know which way they're
want-
doing it?
They're going to tell you that you're going to draw this one, and then at the end, they're going to ask you to draw it 2 more different ways. And I'm just giving you the answer right here. Now,
I'm sorry, the answer to what now?
But one of the questions on that.
it's one of the questions. Yeah, don't leave till you've seen it. Do you see this one? All right. The big vectors are going up this way, and the little ones are going this way. So these are not going to cancel out. This one is going to be polar also.
Okay.
This, the other one was trans because they're across from each other. Do you know what word you use? This is organic chemistry. You know what word you use when they're on the same side?
Poly? No.
Is L, or it's like is something.
No. No. Oh, close. You're close. Cis.
Cis?
C-I-S.
Like cisgender?
Yeah.
Okay.
It's cis. So there's cis trans isomers. Trans is across, and if they're on the same side, it's cis. I'll leave this here so you can look at that later.
I have another. Well, the same question that maybe I didn't say the first time. The bond polarity, so like this one you have an S and an O, which one has more or less?
The higher
The
electronegative.
The high, yeah.
You
So,
point it towards the one with the higher electronegative.
So, but like, how would you
but
do
there's
it?
3. So do you need to list all
Two.
3?
Yeah. If there's 3, yeah, you're going to have to do carbon to carbon, carbon to hydrogen, carbon to chlorine. Yeah.
Oh, okay.
You're going to have 3 answers there.
Oh.
So carbon to hydrogen.
Sorry, I asked.
By the way, this is not due until, I don't know if you noticed that. What did I put, the 18th? Is
Oh,
that
Oh.
Monday? I gave you lots of time to do this. I kind of figured you'd have questions.
You gonna be available over the weekend to answer questions?
Yeah, I'll be in New York. I'll be in upstate New York.
Specifically where?
Newark, ever heard of it?
Yeah.
How do you know Newark?
No. I've heard of Newark, New Jersey. Never mind.
And Newark, yeah, nowhere close. They're like 5 hours.
Anywhere near
apart.
Syracuse?
It's in between Rochester and Syracuse.
Love Syracuse.
Yep. Brother-in-law lives in Manlius or Fayetteville. They're right beside each other. Okay. Does anybody else have any more questions? Do you want me to do another one? Or do you want to try one? Try a couple? I wouldn't leave until you've tried a couple of them when you feel comfortable with them.
I'm gonna do all the ones that look really hard. Okay.
If it's like C,
Okay,
H,
Katie, we're done.
sorry,
Boom.